Today we're going to be talking about a derivative function. So in the previous video, we looked at finding the slope of a tangent line as well as the equation of a tangent line. So what the derivative function is going to do is instead of finding the slope of a tangent line at just one particular point, it finds the slope of a tangent line for any point on the f of x function. So if you look at our definition of a derivative right here, you'll see it looks very similar to the definition we had for finding the slope of a tangent line. The only difference is that instead of plugging in a particular value of c here, we're just plugging in the variable x because it's finding the slope of the tangent line for any x value that we could plug into this function. And then notice over here on the right, we have a few different ways that we can write the derivative. So all three of these notations over here mean derivative. So this first one, we say that as f prime of x. The second one, dy dx. And then this one, d dx of f of x. But all three of those mean the same thing. They all mean derivative, just different textbooks or different examples, you'll see those different notations used. So just want you to familiarize yourself with all three of them. All right, so we're just going to go through a few different examples of using this definition of a derivative. All right, so our first function here, we're looking at a cubic. So f of x is equal to x cubed plus 2x. And all we're going to do is use this definition to find the derivative of this function. So our f prime of x, and I'm just going to stick with that prime notation for now, is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That's just our definition. All I did was copy it down. Now, we're going to plug this into our particular function. So to start with, I'm going to plug the x plus delta x into our function. That would be x plus delta x. Oops, sorry, I forgot my limit here. So the limit as delta x approaches 0 of plugging the x plus delta x in. So x plus delta x quantity cubed plus 2 times x plus delta x, and then minus our f of x function. So minus, and I'm just going to throw it in parentheses for now, x cubed plus 2x. And that's all over delta x. All right. So most of this process of finding a derivative is going to be algebra. So from here out, we have to simplify our whole numerator and then see what can cancel out and just sort of get this thing reduced before we can even worry about taking the limit. So a lot of this process is just a lot of algebra. So we're going to keep going with this. And always just carry that limit out front. All right, so here, if I want to try to cube this, I'm going to do it in steps. First, I'm going to square it, and then I'm going to multiply it again. So I'm just going to square it first. So I'm just going to leave one of those alone. I'm just going to do my x plus delta x quantity squared. So that would give me an x squared plus 2x delta x plus delta x squared. All right. And then this next term, just distribute our 2 in, so plus 2x plus 2 times delta x, and then just distribute that negative through on the end there. So minus x cubed minus 2x. That's still all over delta x. All right. Still a lot of simplifying to do, but right off the bat here I see we have a 2x and a negative 2x, so I'm just going to get those out of the way so I don't have to keep carrying them down with me. And again, just keep bringing that limit down. Okay, so next we have to finish this guy out. So I'm just going to go ahead and distribute my x in, and then I'm going to distribute my delta x in here. So we'd get an x cubed plus 2x squared delta x plus x delta x squared, and then plus x squared delta x plus 2x delta x squared plus delta x cubed. All right, and then just bring these two terms down. Plus 2 delta x minus x cubed. Still all over delta x. All right, like I said, a lot of algebra to do. Okay, so again here, I can see we've got a few things to cancel. We've got the x cubed and the negative x cubed that we can cancel out. And then we've just got some like terms. So I see a 2x squared delta x and an x squared delta x. We can combine those like terms. And we also have an x delta x squared and a 2x delta x squared. So we can combine those like terms as well. We'd have a 3x squared. Let me get back to the other color. So 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x all over delta x. All right, we're getting close here. So now we can cancel a delta x from everything. So this would become the limit as delta x approaches 0 of 3x squared plus 3x delta x plus delta x squared plus 2. All right, and finally, we can take our limit. So if we're looking for the limit as delta x approaches 0, we're just going to plug 0 in for all of our delta x terms, just using direct substitution, and we'll be left with our f prime of x is equal to 3x squared plus 2. And that is our final answer. All right, so this is the process of finding a derivative. Okay. As we get into later sections, you'll see that we have some shortcuts that we can use to take these derivatives a little bit faster, but this is the process that we'll be using for now at least. Okay. So let's go ahead and look at another example. All right, so this time our function is 2 over x. So again, we're going to be looking for the derivative. We'll just call it f prime of x again. So using that same definition, the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. All right, so we need to plug all this into our function. So we get the limit as delta x approaches 0. So the first piece here, f of x plus delta x, that would just be 2 divided by x plus delta x, and then minus f of x, so minus 2 over x, and that's all over delta x. All right, now all of our simplifying before we can worry about the limit. We have to simplify this thing. So since we have a fraction up top, I'm going to go ahead and get all this over a common denominator. So basically just multiply this guy by x plus delta x over x plus delta x, and multiply this guy by x over x to get that common denominator. All right, so this would become the limit as delta x approaches 0. And now this would be 2x minus 2 times the quantity x plus delta x all over x times x plus delta x, and that whole thing still divided by delta x. All right, let's go ahead and clean up that numerator a little bit. So just keep carrying that limit along. So this guy, if we distribute that negative 2 through, we'd get minus 2x minus, minus 2 delta x. It's still all over x times x plus delta x, and the whole thing divided by delta x. Okay, so up in the top here, we can see the 2x and the negative 2x are going to cancel out. And then just remember that whenever we're dividing fractions, we can just multiply by the reciprocal. If we carry down that limit again, we're going to have here negative 2 delta x over x times x plus delta x. And then instead of dividing by this term, I'm just going to multiply by the reciprocal. But then when we do that, we can see that these delta x's just cancel out. And we'll have the limit as delta x approaches 0 of negative 2 divided by x times x plus delta x. All right, so then lastly, we can evaluate our limit. So just using direct substitution, plug 0 in for our delta x. That term would just go away, and we are going to be left with f prime of x is equal to negative 2 over x squared. The only thing that I'm going to add here is that on both the original function as well as our derivative, we have to make sure that we're acknowledging the domain restriction that x cannot equal 0. So that would be our derivative function for this one. All right, one more derivative that I want to do with you guys today. This time we're looking at the square root function. So I'm actually going to go ahead and just put my domain restriction right up here to begin with. Just remember that you can't take the square root of a negative number, so we would have to have x is greater than or equal to 0. All right, so again, finding our derivative, f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. All right, plug this into our function. So the limit as delta x approaches 0 of the square root of x plus delta x minus the square root of x all over delta x. Okay, now in order to simplify this a little bit further, let me just go ahead and copy this down first so I have a little bit more room to work with. we're going to use a technique that we did in the previous unit when evaluating limits with square root functions. We're going to use that rationalizing technique that we did before. So I'm going to multiply by the conjugate of the whole numerator. I'm just multiplying by the conjugate here so we can try and rationalize this. Okay, so then we'll need to multiply this out. And again, just carrying down that limit. So if we FOIL this, we'll get x plus delta x. Our middle terms always cancel with conjugates, and then minus x. I'm just going to leave my denominator in factored form. Okay, so then in the numerator, those x terms will cancel out, which leaves us the limit as delta x approaches 0 of delta x over delta x times the quantity x plus delta x under the radical plus radical x. And of course, the delta x's here cancel out, which will leave us the limit as delta x approaches 0 of 1 over the square root of x plus delta x plus the square root of x. And then finally, we can take our limit. So just using direct substitution, plug 0 in for our delta x's, and we would get 1 over the square root of x plus the square root of x, or we could actually just simplify that. Let me just change that to 1 over 2 square root of x, and that would be our derivative function. Now, again, we have to think about the domain restriction that comes along with this. So originally up here, our function f of x had the domain restriction that x is greater than or equal to 0. It's a little bit different though for the derivative. So if we think for a second about our square root function, you know that the square root function looks something like that. Now remember that a derivative is finding a limit. So in order for the derivative to exist, the limit has to exist. But if we think about this point right here at 0, 0, if we were to try and find a limit of that point, it wouldn't exist because the function doesn't exist on the left-hand side, meaning the left-hand limit itself wouldn't exist. So we're not going to be able to include the whole x is greater than or equal to 0 because at 0 itself, that limit won't exist. So our domain restriction on this derivative is simply x is greater than 0. So anytime you have a function like this, like a square root, that just starts abruptly at a point right here, the derivative will not exist at that first starting point because the limit doesn't exist on the other side of it. All right, so that leads us into a couple other examples here where we're thinking about our derivative and where it may and may not exist. Okay, so let's take a look at this example 6a. So you see we have this absolute value function drawn out here, and I want to look specifically at x equals 2, which would be this vertex point right here. Okay. All right, now again, think about the fact that a derivative function is finding the slope of the tangent line. So with this one, if we were just to think about the slope of this function, so everywhere over here to the left of that vertex point, our slope would be -1. But then everywhere to the right of that vertex point, our slope would be a positive one. So then that asks the question of, well, what would the slope be at that vertex point? So it's just changing abruptly from -1 to +1. So because we have such a sharp corner right here and this abrupt change from one slope to another, our derivative does not exist at that vertex point. Okay, so here the derivative does not exist, or you could say is undefined at x equals 2. And the rule here is going to be because there is a sharp corner or a sharp turn. Okay, anytime you have a sharp turn in a graph like that, the derivative is undefined. Okay, now here's another one. So this time we're looking at the cube root of x at x equals 0. Now again, think about the fact that a derivative function is finding the slope of a tangent line. Well, if we want to think about the slope of our tangent line at that point 0 right there, right in the middle, our tangent line would be a vertical line. But the slope of a vertical line is undefined. And if the derivative is finding the slope of a tangent line, then the derivative is also undefined. So we'll say since the tangent line is vertical, the slope is undefined, and therefore the derivative is undefined. All right. One more example I want to look at here, where we have some issues with differentiability, is this rational function, and we want to look at x equals 4. So if you think about x equals 4 right here, you'll see, of course, that we have a vertical asymptote at x equals 4. Well, if we have a vertical asymptote, that of course means that our function is undefined at x equals 4. So since the original function is undefined at x equals 4, the derivative function is also undefined at x equals 4. So since f of x is undefined at x equals 4, the derivative is also undefined. So the rule here is that the derivative is undefined anywhere where there is a discontinuity in the graph. The derivative is undefined anywhere with a discontinuity. Okay, so these are all of our examples of issues with differentiability. The first case where our function is not differentiable, meaning you can't find a derivative, is at a sharp turn. The second instance that our function is not differentiable is when you have a vertical tangent line. And the third instance where the function is not differentiable is wherever your function itself is undefined or your function is discontinuous. All right, guys, so that is the introduction to derivatives. Keep watching the other videos if you want to find out more techniques for finding them.